So Descartes' rule of signs. I'll start with an example. Let's see. Famous x minus 2 equals 0. Does it have a sign change in the coefficients? Yes. What is the sign change? Positive to negative. So as you go from here to there, you have one change. And that is f of x. So since it has one sign change, this would imply one positive 0. Good. Well, do we agree that it has one positive 0? X minus 2 is 0, which would imply x is equal to positive 2. Now, if I did f of minus x, what will I get? Negative x minus 2. Correct. But you're changing the function in time. You end up having negative x minus 2 equals 0. Which would imply x is equal to negative 2, which would be the negative 0 for f of negative x. So in this case, we can radically change the sign. So the key to note, one sign change, one positive 0, if you're looking for positive zeros. If you want to look for a negative 0, then you would go and start with f of minus x. But we know x minus 2 doesn't have negative zeros. No negative number when you put in there is going to give 0. Do you agree? Yes. So this particular step applies if you think that there would be or there could be a negative 0. So there is only one positive 0 and we're done. To start with that case, and you look at the equation. Of course, that is a simple quadratic equation to it. So, what is the easiest way to solve? Quadratic formula. Easier than that. If you can't do it,
just look at it.
What do you mean by look at it?
It's like, and it just seems so simple.
What makes it so simple?
It's just 3 times 2 and then you're
Factoring. So what he says it's so simple is factoring. Yes. So the initial method is factoring. If you can't see it, then you can't factor. So you move on to the next case, which is the quadratic continuum. Well, does it have a sign change? No. So perhaps this particular equation doesn't have any positive zeros. So let's start with negative zeros. Does this have any negative zeros? Well, In order to do that, we are going to go back to this. Also, in this one, I forgot to mention, we changed it to minus x. We didn't have any sign change at all. That's never. So, since we don't have any positive zeros, I'm going to replace x by negative x. But prior to doing that, what should you do? Going back to that thing. Parentheses. So minus x squared plus 5 times minus x plus 6. Negative x, if you square it, what do you get? X squared. 5 times negative x, negative 5x plus 6. This time, do you see any sign change? Yes. So I see one here and another. So in total, we have 2 sign changes. And we recognize that it would have 2 negative zeros. Does it tell you what the zeros are? No. All it can tell you is if it is going to have positive zeros or negative zeros. Key thing to note when we say negative zeros, positive zeros, we only mean real zeros. We're not talking about complex zeros. No complex zeros, only real. So let's be specific with real. What are the 2 zeros? How about negative 3 and negative 2? Is it negative 3 and negative 2? Does that give you x squared plus 5x plus 6? Yes. No, it's not. How about x plus 3 and plus 2? That is set it equal to 0. You get negative. So it's not that one, this one. We have 2 roots. One is negative 3. The other is negative 2. When you write it as a factor or as factors, it is x plus 3 times x plus 2. Good. What if you're not able to find the zeros? What should you do about the mission?
Using for the quadratic, like just quadratic formula.
We can use the quadratic formula in this case. What if you had a cubic polynomial of some sort? You start with, rational root theorem, synthetic division, one of those. Again, these are methods that are in place when you don't use a calculator, when you don't have the opportunity to use the calculator. You have the calculator, it is going to make things easy for you. Are we clear? So, Descartes' rule of signs suggests a way to find the number of positive real zeros, the number of negative real zeros for a polynomial function based on the sign change. Good. And once again, only real zeros. If you think that it would have positive real zeros, here's the proof. First rule, you look for the number of sign changes. That would imply the number of positive real zeros, which is a case we did. There is yet another possibility. So you can look at the number of positive, the number of sign changes, and you look for whatever value that is exactly one even integer less than the number of sign changes. One last condition. There is a case that I've started with, which is a separate case in and of itself. So if you have exactly one positive sign change, then there will be exactly one positive real zero. Good? Yes. And before we move on, this is for a polynomial of the form f of x equals 0. Under these conditions, use f of x. If you realize that the polynomial doesn't have any positive zeros, perhaps it has negative zeros instead of real zeros. So what is the rule? You go for f of minus x if you realize that f of x doesn't have any positive sign changes. So in this case, we have to use f of minus x. You have to replace all the x's by negative x. The process is the same. Going to A. Number of sign changes. Result in, you tell me. Go ahead, number.
The number of negative real zeros.
Number of negative real zeros. Take a guess. Point to B. I just want you to guess. You can be wrong. I might choose my guessing mind and say, well, positive became negative. So number of sign changes minus a negative even integer, that would imply the number of negative real zeros. Logic, right? But that's wrong. Why? number of sign changes minus a negative integer would make it plus, correct? We end up having more zeros than what we should actually have. So the second pointer is the same. We simply look at the number of sign changes, reduce it by a positive even integer. That will give you the number of negative real zeros. Good. The very last case, take a guess. Don't know why I said positive sign change. Just a sign change, right? Exactly one sign change. Wouldn't I exactly one? Again, one can only look at real zeros. Complex is not going to work. I am sure maybe there's a theorem of some kind in complex analysis, but that is not my discipline. So that is not my area of expertise. So I don't know. You can Google it. Maybe there is something. Oh, we can. Yes. Then, all we want to do is to determine the number of positive zeros, the number of negative zeros. We're not going to do anything else because we've done other approaches like the root theorem, quadratic formulas, synthetic conversion, linear factorization, all kinds of fun stuff. So, look at that equation. How many positive zeros does it have? What? None. Alexa says none. One.
Does not change.
What does not change?
The sign.
The sign doesn't change. We don't have any sign changes. So it's just zero. Now that we've accomplished that part, the next reasonable question is to ask, well, perhaps it has negative zeros. Yes? If that doesn't work, then what is our final conclusion? There are no real zeros. But logic again. This is a third degree polynomial, so it must have one real for sure. Why is that? Because complex zeros always occur in conjugate pairs. So one of them has to be real, and that will be negative. So to do that, f of x, we are going to change x by negative x. What should we do? Parenthesis. Of course, you may choose not to use parentheses. I don't care, as long as you get it right. Minus x cubed, negative x squared would be positive x squared times 7, positive 7x squared, positive 1 times negative x plus 7. How many sign changes did you say? 3. 1, 2, 3. Yes. So how many positive, negative zeros do we have? 3. And that would give us the conclusion that none of the zeros would be complex. Yes, so all of them are real. So don't just put the answer as 3 zeros. We all know it's not 3 zeros. That would defeat the purpose of the rule. How many sign changes do we observe? Minus the plus 1, 2, 3. And all of those 3 sign changes occur for the original function f of x. This would mean there are 3 positive real zeros. Good. The second pointer that I wrote, which is number or item B, in both cases, that would typically be very useful if you go for higher order polynomials. Because if you had only 3, things are easy to deduce, yes? But if you go for 5th degree, 6th degree, 7th degree polynomial, that's when pointer B come into play. Good. Okay. Okay, so the number of sign changes, in this case, we have 1 positive, negative, negative, positive, positive, negative, 3 sign changes. 3. So even before you start the problem, look at the polynomial, get an idea. This is a 4th degree polynomial, and you have established 3 sign changes for the original function f of x, which would simply mean 3 positive zeros. So the possibilities are 3 positive zeros, real zeros. That is based on just pointer A, correct? If you use pointer B, the deduction would be, well, you've got to reduce it by 1 positive even integer. Well, what is the first even integer that comes to your mind? Two, right? What is 3 minus 2? 1. So the conclusion would be only 1 positive real zero. If you use pointer B, well, if you pick 1 positive real zero, that would mean the remaining has to be all 3 of them negative, yes? 3 positive real zeros would mean 1 negative real zero. So let's say if you have 1 negative real zero, f of minus x, before you start, what should you do? Parentheses. Full negative x raised 4, negative x cubed plus 5 times negative x squared minus 2 times negative x minus 6 equals 0. Good. Well, full x raised 4, negative x cubed times negative positive x cubed, 5, and negative x squared, if you square, the negative goes away, 5x squared plus 2x minus 6 equals 0. Good. And that would imply, well, you have one sign change, and this is f of minus x. Exactly one sign change would mean exactly how many negative real zeros? So, rule A, one negative real zero. Zero. We can't even use rule B, correct? Because if you have one sign change, first of all, you can't subtract net 2 and say, I have negative 1, 0. Not possible. Another condition is rule C. What does rule C state? If you have exactly one sign change with f of x, you have exactly 1, 0. If you have exactly one sign change with f of minus x, you have exactly 1 negative root 0. So that doesn't even apply. So the conclusion is you have 3 positive real zeros, 1 negative root 0. And you cannot leave it just here. That's awesome if you do that. If you just left it there, then you are suggesting that the next root is x is equal to 0, correct? Yes, because x is equal to 0 is neither positive nor negative. I'm picking x is equal to 0 because that one root cannot be complex, because complex roots occur in past. Well, if you plug in 0 here, will you get 0? 0, 0, 0, 0, all of those terms will go away. We'll have negative 6. Is negative 6 equal to 0 in this world? No. So, not feasible. So you can't solve here. You have to check for the next condition. Yes? And that would end 2.5.